That's a great question. So conventional DBS, as you know, uses just continuous stimulation. The theory is that, acts via kind of two different mechanisms. One is suppressing pathological oscillations, meaning, abnormal rhythms that the brain gets synchronized into when somebody develops Parkinson's disease. So they kind of get stuck in a slower, more rigid, more like frozen state. And what conventional DBS does is that at these high frequency signals, it kind of suppresses a motor, this abnormal signal. So basically freeing up the patient's ability to move and respond to motor commands, so allow them to move. So they can move easier, faster. And tremor suppression may work via different mechanisms. So the brain is stuck in a different rhythm for tremor. And traditionally, I think all these symptom improvement with conventional DBS works really well to treat arm and leg symptoms. So more, axial, meaning like central symptoms that involve the trunk, the neck, and the head. Um, these DBS, just for whatever reason, doesn't really improve those functions. It's could be that, we're not targeting the part of the brain that, really treats those. And I think for most patients, again, it's the ability to move their arms and legs that they want improvement. So that's why traditional DBS works well for those symptoms. But then on the other hand, I think the other main thing that differentiates gait balance falls from, things like tremor, rigidity, bradykinesia, slowness, is that gait is a highly, highly dynamic state. As we're walking, we're constantly coordinating complex movements, muscle contractions across all four limbs of the body, where each leg is alternating between, standing and swinging. And we're, taking environment, context, a lot of other information processing at the same time. So one caveat of this continuous stimulation is, again, it's just at a constant rate, constant amplitude. So it doesn't adapt to the dynamic changes that's happening in somebody's brain as we're performing these complex movement. And one of kind of the cost and potential, you can think of it almost like a side effect of continuous stimulation, is that it also suppresses these more naturalistic, uh, normal signals in the brain that's, passed from different areas to coordinate movement. So that's why I think for more complex movements, the stimulation has to change or dynamically alter in response to that to allow more of these physiologic symptoms or signals to come through. Yeah, so traditional DBS, as I mentioned, just the clinicians, neurologists set a certain rate, certain frequency, certain amplitude, and then they test the patient in clinic, and it seems to work, and then they go home with that. So what our group did that's really novel is that we, in addition to the deep brain stimulation electrodes, we actually put some surface electrodes on the surface of the brain that can record and capture signals associated with walking. So we're trying to detect signals, biomarkers of when somebody's about to take a left step versus right step with the right leg. And we capture these dynamic, sub-second activities. And what we're doing is rapidly changing amount of stimulation that each patient is receiving in his or her brain hemisphere in accordance with a gait cycle. So, we can, either decrease or increase stimulation as they're about to take a left or right step. And we're kind of coordinating this changes across the two hemispheres. So that in itself is a, really challenging technical achievement that we're able to perform. And I think that in itself is, worth noting. And that's how it's very, very different from normal DBS.